Hey, everybody. Happy Friday. Thanks for being with us. Thanks for joining us on our first webinar of 2025. Drew Morgan, principal at BHP Structural up in the Boise office. Just a quick introduction to BHP for those of you who might not know who we are. We are a full service structural engineering firm with, we're licensed in all 50 states, offices in Idaho and Utah. 60 employees across all those offices. We work in every market sector that you work in, and we have worked with several of you, and we hope to be able to work with more of you. We do that with this promise. We promise to be responsive. We promise to have well-coordinated drawings, and we promise to use our creativity to help your project become a reality. Announcements next month. We'll have another webinar towards the end of the month on lateral steel options. So look for more information on that to come. For today's webinar, we'll do what we've done in the past, where we have that Q&A box up at the top. That'll be your place to interact with us. We'll put information in there for you, and if you have questions, put them in there. If they're about the content of the presentation, we'll save them to the end and answer them all at once. If you're having technical difficulties, put the questions in there and we'll try to help you in the background while the presentation goes. Also in that box is where at the end of the presentation, Amber is going to put a link to go fill out a form so you can get your continuing education credit. I think we're going to experiment with the QR code this time too, so watch for that at the end of the presentation. I think that's it. So we'll just move on to the reason you're here for the content. We've got with us today Marty Olson, who's a principal in our Salt Lake office. And we're also joined by Ilya Alyoskin from LUHA Build. And I think he's up and he can introduce himself and his firm.
Thank you, Drew. Everybody, happy Friday. I'm excited to join BHP Structural for this presentation. Just a few words about our company. I'm the founder of the LUHA Facade Solutions company, and our business model is to design, supply, support facade solutions. And when we talk about facade solutions, what do we mean by that? Is that we encompass different cladding materials and attachment systems, and we do design and engineering with BHP support for those cladding materials and attachment systems. So we're a full service distributor of these types of products, and we carry different cladding materials such as ceramic, terracotta, GFRC, extruded aluminum panels, formed metal panels, expanded mesh, sintered stone, and some more options. We're constantly researching more and adding more materials as the need arises. And as far as the attachment systems goes, we carry everything from the back of the panel to the substrate, and our attachment systems are thermally broken, non-combustible, recyclable, or reusable at the end of its life. They're also adjustable, meaning as the substrate tolerances are present, our systems are adjustable for in and out. And we have aluminum as well as stainless options for better thermal performance. And we also have adhesive bonding systems, basically relying on adhesives versus mechanical fasteners for the cladding attachment. And the topic of today's presentations is Rainscreen cladding, the design principles for resilient and sustainable facade. And the course description is such, basically Rainscreens, they perform many different functions. We control the air and water infiltration. It has to be structural performing. And it has aesthetic qualities as well. So the course goals is that we'll review the new code requirements for high-performing facades, and we'll share how it relates to the attachment systems available on the market, and pros and cons of each attachment systems. We will review how structural performance of the system can directly affect sustainability. This is kind of a special topic and that we developed is we feel that sometimes in the facade design, the two topics are not thought of as something that helps each other, but we believe that with clever structural design, you can create highly sustainable facades, and we'll show you how. And we'll also review different cladding materials and kind of limitations, pros and cons of each cladding material. And yeah, and then a special topic would be talking a little bit more in depth on perforated metal panel design. So why are we talking about these new code requirements and new, more high-performing facades? Is because of ASHRAE 90.1 2022 edition has introduced new requirements addressing thermal bridging and enhancing building energy efficiency. And what that means is that the jurisdictions and cities and states that adopt these building codes, the new versions, are going to need to perform thermal bridging analysis in order to meet the code. And just real quick about thermal bridging. So in general, you have linear thermal bridging, which is structural elements that are cutting through the building, through the insulation layers continuously. These could be like a balcony is a perfect example. If it's attaching through to the slab without any kind of breaks, that's a linear thermal bridge, or maybe there's a canopy and structural supports running through. That's a linear thermal bridge. Those need to be addressed in thermal calculations. And then there's point thermal bridging, which is what we deal with in the cladding design. Is these are screws, fastening points that are penetrating the insulation, and they also affect the effective R value of the insulation. So they reduce it. The more screws you have going through the insulation, the more reduction in the R value. And just a disclaimer, I'm not a thermal engineer, but just speaking from experience by having done several thermal simulations for different products, as well as being involved on different projects and how that relates to the structural design. This is kind of how we're trying to bridge the two. The ASHRAE 90.1 2022 will allow you to be code compliant. Basically, you have a prescriptive approach where you have prescriptive R value that you can assign to certain things, or you can have a performance-based approach, which is sometimes called a trade-off method. But essentially, we analyze the whole building envelope as a whole, and we analyze the roof, the windows, the opaque cladding, and we can say, well, if we adopt a more efficient strategy in one place, we can trade it off in a less efficient place, strategy in a different place. So we add more insulation, or we use a thermally broken system in the wall. Now maybe we don't have to use a triple glazed window, et cetera, et cetera. So this trade-off method is a more flexible approach and gives designers more flexibility to be code compliant. And again, we're talking about this in the framework of Rainscreens, and we've done previous presentations where we dove into kind of each feature of the Rainscreen, so I'm not going to spend too much time here. But here on the graphic, what you can see here is number 6 is the cladding. The cladding keeps majority of the water out of the building. And the water kind of sheds on the face of it. However, Rainscreen is also an open joint system. Some of the water will get behind the cladding, and behind the cladding is a vented cavity, which is the number 4 on the slide here. And the vented cavity allows for the water to drain in the back and ventilate out. Yeah, this is one of the main features of the Rainscreen wall, and it allows for the walls to be long-lasting, high-performing. And then you have exterior insulation, which is number 3. Again, we want to move as much as insulation on the outside as possible. And number one is the vapor drive from the inside. It's allowing to escape to the exterior and ventilate out. So Rainscreen's walls are really the way to build, and most of the projects we're working on do feature Rainscreen wall assembly, but there's still a lot of unknowns in terms of the code and the requirements. And there are organizations that are trying to make it more commonplace and more of a code language such as RAINA. And we've spoken to several organizations overseas that are really trying to standardize the language as well as the requirements for these rain screens, because the current building code still is not super clear about how these need to be constructed. And what does this new code requirements mean for the rain screen walls is that, well, number one, we already talked about it, thermal bridging will have to be calculated. And therefore, using continuous metal girts is it's going to be less and less possible just because they're not thermally efficient. We're also going to see deeper rain screen insulation. 8 inches deep is coming. We're seeing this in the places that have adopted the stretch code, such as Boston, New York. We're seeing deeper and deeper mineral or just the exterior insulation in the cavity, and that's coming more and more commonplace. And also, we're going to have less structural supports, again, to reduce thermal bridging, which is going to lead to more sustainable options because you're just using less material to bridge that insulation. I'm going to turn it over to Marty here.
Thanks, Ilya. Yeah, so I'm a structural engineer, and the greatest challenge with these rain screen systems is how do you hang all of the cladding and the cladding weight off of the main structural wall through the insulation cavity. Now, metal is stronger, aluminum stronger, and in the past 10 years, traditionally, we've used metal girts to bridge the insulation. However, with the new ASHRAE requirements, this just isn't becoming feasible anymore. They want more stringent code requirements for the thermal bridging. So what we're seeing a lot of right now is fiberglass pultruded Z-girts. And these have the advantage that they're resistant to thermal conductivity, but they do have enough strength to bridge the insulation and hang the cladding weight from the main structural wall in the back. The slide here shows a typical exogirt or a strong girt. You can see kind of from the dimensions how they are. The trick about pultruded Z-girts is it's basically a fiberglass coated in resin. And the way the fiberglass strands run is typically along the length of the extruded piece. So that means they're strongest in the direction perpendicular to their length, and then they're going to have an inherent weakness when bending across that fiber in the perpendicular direction. So when you hang a Z-girt against a metal stud, the problem with it is it's not as strong in that direction for the weight or the gravity of it. So we've got to be careful in terms of how much weight we can put on these. Horizontal installation would be to run the pultruded girt across the studs, as you can see in this image here. I recommend this for lightweight systems. So generally speaking, 5 PSF or less, which is essentially metal panel systems, not anything heavier than that. And that you can usually get to work and adjust the spacing of the Z-girts as necessary to hold up the weight of the cladding. If you want to hold up larger weight, pay attention to the detail here where now we put the orientation of the Z-girt parallel to the stud. This has the advantage of now we're loading the dead weight of the cladding parallel to the strong axis of the fibers in the Z-girt. So this has the advantage that it can hold up to heavier, 14 PSF systems like terracotta or stone. And so detailing on how that Z-girt's placed is kind of key. Fiberglass pultruded clips. So it's basically like just a clip with a Z-girt. These are really popular for a couple reasons. The fiber in these are extruded along the length of the clip, and these have the advantage that you can run your tracks, your outside tracks, either vertical, as shown in the top image there, or horizontal. So that gives you a lot of flexibility in terms of, you know, you can just spec one clip. We can figure out the spacing of them to hold up the weight, and then we can run rails either horizontal or parallel depending on our layout of our panels. Again, these can hold up larger weighted systems, and you don't necessarily need to know the direction of your cladding and how it's supported if you spec these types of clip systems. I mentioned metal clips before and how they lose the thermal ability. However, you can get some thermal efficiency out of them by doing one of two things. You can have a thermal pad on the back side of these. These are just a thermal barrier between where the screws go back into the stud. That gives you some protection against thermal resistance. The other thing we're seeing a lot more of is stainless steel clips. Now, stainless steel clips are going to be more pricier, but they have two advantages. Is that one, you can usually space your clips further apart because the stainless steel is stronger than the fiberglass. And two is that stainless steel doesn't have the same thermal conductivity values as aluminum does. So you can actually space these out further and acquire the same R value as you would doing much more pultruded clips everywhere. So all those we're kind of talking about the backup substrate being metal studs. When we're attaching to masonry or concrete, a couple things to keep in mind. Usually the way these are always done is with a vertical T or L angle that attaches to dead load and wind load clips. And the reason we do this is the backup wall is extremely rigid. So your system as aluminum rails are going to be expanding and contracting under the thermal effects of the sun. And that wall behind there isn't going to move at all. So we need to allow the system to breathe. And the way we do that is we hang a dead load bracket off the top rail. So the rail hangs from the dead load bracket. And then we attach wind load brackets or slip conditions that allow that thermal rail to move and breathe. Here's kind of an image showing the plan view of that. You can see the T-rail in plan view section attaching to a dead load clip where the screws are in the non-slotted holes. And then all you'd have to do to make that a wind load clip is just attach the screws in the slotted holes there. So it's key to remember that all these systems expand under the thermal heat of the sun, and we need to make sure we're allowing the Rainscreen system to breathe, not just for moisture, but also to breathe for thermal expansion. Now I'll turn the time back over to Ilya.
Thank you, Marty. So I want to speak about the consideration for thermal analysis, again, when we analyze these cladding attachment systems. Again, I'm not a thermal engineer, but this is what I've seen in terms of what's happening. Is 2D versus 3D thermal analysis. When we're analyzing these wall assemblies, my understanding is that the two-dimensional method doesn't allow to analyze many different conditions, and we operate in a three-dimensional world. So we really want to use a 3D therm software to analyze these conditions. And when we talk about performance of the wall, it's also the average of a certain area. So in a window, it's a lot easier to do because you have the edge of the frame, the center of the glass, and then you kind of average out that condition. In the Rainscreen wall, it's kind of similar, but basically you analyze the conditions where you have the clips or the girt attachments, which is going to be your worst condition thermally. And then you have analyzed the other areas, and kind of the weighted average of the whole is your performance of the wall. Also, when we're doing the thermal analysis of these things, many assumptions are being made, and many things affect the thermal performance, such as even different cladding materials. Metal warms up and cools off much faster than, let's say, clay terracotta panels. We have fasteners. Are they steel fasteners? Are they stainless fasteners? What is the air space, and what are the assumptions made for the insulating value of the airspace, et cetera, et cetera. So when these thermal engineers perform these, there's a lot of assumptions that are being made, and you can get drastically different values based on these assumptions. So again, it's sort of a mix between art and science and how this information can be presented. And as far as the strategies to mitigate thermal bridging, for example, one of the areas I'm going to show you here as a wall assembly that we have analyzed. And if you could see here in the diagram of the system, you can see that the vertical rail is cutting inside the insulation, and that is critical to the thermal performance. So if we have room and we can pull that T-rail completely out of the insulation, the thermal performance of the system goes up dramatically. But in this case, we're trying to do a more of a expected case scenario where the T-rail would be intersecting the insulation. Those are the values that we derived. And these tables that are shown are basically, without going too much into detail, but here we analyze two different configurations, and they have to do with the spacing of the clips. Configuration 1 is we have the spacing 16 on center, which means attaching to every stud, and then 26 inches vertically. And then in configuration 2 is 32 on center, every other stud, and 36 vertically. So two different configurations, and we can see that the values we're getting are quite different. And the last column is the percent insulation effectiveness, or pi, is how effective the assembly is versus the nominal R value. Let's say in the case of 4 inches of insulation, we should be getting 20 R value. And in reality, configuration 1, we're getting 15.9, configuration 2, we're getting 18. And then it's presented as a percentage. So you can see how the spacing of the brackets, same system, same components, same materials, but just the spacing of the brackets creates 10% difference in effective insulation. So it's not always just what materials are we using, fiberglass, stainless, aluminum, but also how often we're using. And that's really important to consider. So next topic would be the veneers and their attachments. We're not going to have time to go through all the veneers, but we're going to talk about the most popular ones and kind of what we see throughout our line of work. Number 1 is visible versus concealed attachment system. So the proof is kind of in the name. The visible systems is you will see some kind of an attachment method on the exterior of the panel, and that's usually going to be a screw, a fastener head, or a small clip that you'll see. And generally those can be color matched to the panel. So at a certain distance and a certain height of the building, you're going to lose those screws or clips, and it's really an economical way to attach panels. And then the concealed attachment systems is something that you don't see. So there's some kind of an anchor behind, or maybe it's an adhesive system behind, but basically the attachment method is now concealed from the viewer. Architecturally speaking, that's preferred method. However, it's also more expensive because you have more components, more labor on site, more pre-drilling of the panels that need to happen. So those are the two considerations. I would say one thing about the visible system, while it's easy to execute, you basically have vertical rails and you fasten the panels directly into those rails. What happens a lot of times is that, and Marty mentioned this about allowing the systems to breathe, is that the panels, they also move. And depending on your cladding material, for example, HPL, high pressure laminates, they move. Every material has some movement in it, and you need to allow for that movement to happen. And we need to oversize the holes in the panel and have the screw run in the center of the hole. And only 1 or 2 connections per panel can be fixed. In essence, the hole could be the same diameter as the screw. The rest need to be flexible and allow for this panel to move. And we've seen failures on other projects because this was not considered, as everything is hard fastened. And now aluminum is moving, the panel is moving, there's nowhere for it to go, so it breaks the fasteners and the panels fail. So yeah, that's kind of my 2 cents on the visible system. Next is the aluminum composite and aluminum plate materials. Aluminum composite is still a popular choice. However, many architects, designers are moving away from it due to the fire concerns. Of course, in response to the fire, the ACM industry has introduced a fire-resistant core as well as A2 core, which is a mineral wool core. So those prevent the spread of fire. However, just because of the tendency, plate material is used a lot more now because of this fire concern. But essentially, when you're attaching ACM systems, you can have two approaches. You can do a wet set method, which essentially is using sealant inside the joint, and then you have a dry set method, which is using some kind of extrusion, and then you have a spline and the same color attached behind it, so your joint is nice and consistent color. Again, the wet set system is usually a much simpler way because you just have a Z-clip and you fasten it and you caulk it. However, because of the caulking, now you have the labor to install the caulking, and then you need the labor to service the caulking. Every 5 to 10 years, you're going to replace that caulk joint. So it's not really ideal for that. So dry set systems are more and more popular. Now you can make them in a way where you can attach panels independently of panels around them. So it's a non-sequential dry set system. And for fire requirements, you need to do either dry set or wet seal, and not kind of an open joint such as you would do with a non-combustible cladding. Then single skin metal panels is still a popular option. They can be either extruded or roll formed. Roll formed is by far a more acceptable method just because it's economical. Yeah, it's mostly just because of the cost, and you can get fairly thinner gauge materials. Now, one comment on this is that if it's a roll form panel and you have a large flat surface, almost inevitably at these thinner gauges, it's going to start oil canning. So introducing corrugations into the face of the panel really is going to help this oil canning issue. But as far as the attachment of the panels, single skin metal panels, also you can do a face fastener. That's the most kind of simple widespread method. And or you can do a clip that allows for a concealed method of attachment. Pre-engineered honeycomb panels, that's another way. So these are non-combustible, and you introduce a honeycomb, and you can have very, very large panels with no oil canning. They're very rigid. Also an option to clad the building. And as mentioned, we're gonna do a little bit of special topic on perforated aluminum panels. One, because we see it growing in popularity, and two, because we see kind of the same mistakes or just assumptions that are being made during the design phase. But essentially, what's happening with these panels is that if we look at the advantages, is that the perforation, because we're putting holes, it reduces wind pressure because now the wind is able to pass through. And then you can allow these pixelated effects, different sizes of perforated panels onto the building. So these are the advantages. However, now you have holes in the panel, and the stiffeners you're able to see the stiffeners. And now you need to introduce heavier gauge aluminum in order to counteract the force, because even though you're reducing wind loads, you're also weakening the panels by putting holes in the panels. So when we see designs, these panels tend to be fairly large, 4 foot wide, 5 foot wide by 10 feet tall. And at those thicknesses, you really need to go 3/16 or even 1/4 of an inch thick in order to counteract the wind loads. Otherwise, you're going to have so many stiffeners that this perforated panel is going to lose its appeal of perforations because you're going to see stiffeners all over the place. And what we see a lot of times, something being designed maybe 16 gauge or an 1/8 inch. And when we go to calculate it, when Marty runs the calcs, we find out that those panels cannot be structurally sound. So we need to do a lot of stiffening or thickening the material, and nobody has the money in the budget because they bid it at 1/8 or 16 gauge. And now we need to go to a thicker gauge, more stiffeners, et cetera, et cetera. So that's something really we wanted to drive to the community here, is that these perforated panels, they're usually thicker. They need to be thicker than you think because they become weaker because of the holes. And then as far as the attachment of these perforated panels, this is kind of the most typical way. If you can have perforations towards the perimeter of the panels, you can use those perforations to attach them into the structure through the perforation hole. Again, it's sort of a visible just because you're able to see through the perforations. However, sometimes you can introduce, such as you see here, is a hook and pin type of attachment. That's a way to do it, or maybe a special joint that if you don't have the perforation towards the edge, you can do other methods of attaching in order to achieve the satisfactory attachment way. And then the next panel is clay, ceramic, terracotta. Why did I put slashes between those things? Because we see it all the time. So the terracotta and ceramic are really one and the same thing, and it's made from clay. It's a fired clay product. And when we talk about ceramic and terracotta, again, it's one of the same material, but it's all about the water absorption rate. So you have brick that has high absorption rate, then you have ceramic, then you have porcelain, and it's all clay and almost the same materials that are mixed together and fired at high temperatures. But the water absorption is what separates those materials from each other. And then in general, clay and terracotta, it's a very versatile and beautiful material, and the designs are now getting quite elaborate with many different three-dimensional sizes. But in general, most of the systems on the market will going to feature either some kind of a clip that holds the edge of the panel, such as you see on the left, or what you see on the right is a vertical rail that has pre-punched hooks, and the panel has grooves in the back, and they basically snap into each other. So those are the two main ways of attaching the clay terracotta panels. Then GFRC / UHPC. So those two, they're very similar products in terms of how they look. However, the method of achieving GFRC is a sprayed method, while UHPC is a cast method. And there's subtle differences in strength of the materials, etc. But in general, when we talk about the attachment to the building, this is a pretty standard system here for either GFRC or UHPC. It's an undercut anchor that's attached to a clip hung on a horizontal rail. Or in case of GFRC, you can cast these frames. Actually, UHPC as well. In some cases, you can cast these frames in the back of the panel, and then that frame gets hung onto the building onto only, let's say, 4 attachment points. Natural stones, most natural stones fall into these categories. And these different stones, they vary wildly because of their nature, on how strong they are, their flexural strength, their compression strength, and not all of them can be used on facades. So granite is kind of the most versatile. Granite almost always can be used on exterior cladding. However, the other ones, they really need to be analyzed. Marble, limestone, sandstone, how they can be attached onto the building. But in general, what we see is 3 types of attachments. You have a kerf anchor, a pin anchor, and an undercut anchor. And the pin anchor is essentially a dowel or a pin that's coming out. And so there's a hole in the edge of the stone, and you set the stone over the dowel. The kerf anchor it has a continuous or a segmented slot that's cut in the edge of it, and there's again a clip that goes in the edge of the stone. And then you have undercut anchor, which is the same as what we looked at, the GFRC attachment. You have a back anchor. So yeah, I mean, there's hundreds of different materials on the market, but essentially it's going to be featuring one of these combinations of attachments. And so I'm gonna pass this over to Marty for the glass Rainscreen panels. I think you're muted, Marty.
Yeah, so believe it or not, there's glass Rainscreen systems. Generally speaking, the glass is going to be opaque or colored. The reason for that is the way we hang these is generally a silicone method with rails on the back side of the glass. So it's really particularly important that those rails and the silicone be cured in a factory setting, because there's very specific requirements to get the structural capacity out of that silicone, and make sure we're able to achieve through that silicone bond the expansion of the aluminum rail behind the glass. Glass doesn't tend to expand. It's the aluminum behind it that wants to. And so if you don't have enough bite on that silicone, you'll pop that rail right off when it heats up. So you really got to be careful with glass facade systems. But in general, they kind of work as a hook and pin system with the back rail. And then they just kind of go up, hook and pin, and attach to the rest of the rail system there. Kind of on a similar note are polycarbonate panel systems. These are basically plastic sheets. And the advantage of these is you can light them up from behind and create light box and shadow box effects. The one thing you need to be really careful with polycarbonate is it's highly, highly expansive material. So when this is out in the sun, this is your most expansive material out of any of the products that we've shown so far. So what that means is if you're going to use exposed anchors, typically they have a standoff anchor as pictured in number 4, with these huge barrel caps that allow for an oversized hole so that you can really have that thermal movement occur and not engage your attachment source. The other way to handle these is to place them in a continuous extrusion, as you can see kind of in number 3 and number 2, and make sure you just have enough room and gap in there to allow that panel to expand. The other one good thing about polycarbonate systems, and I've dealt with this on a couple projects, is they're actually good for a small blast rating for shrapnel. Keep in mind, polycarbonate is what's used in bulletproof glass. So it's a thin film of polycarbonate that's laminated onto the glass, and that's what absorbs the bullet puncture. So if you have any kind of blast design buildings, these can handle some mild bits of shrapnel. Special topics. So regardless of which cladding system you choose, any one of these special topics will apply. The first one we're going to talk about is in general corrosion. So Rainscreen systems have the cladding barrier that prevents most water from getting through into the backside of your building, but some water is going to get back there. And when we talk about corrosion, there's regular corrosion or oxidization of steel, which is shown up in the top picture. That's just normal corrosion. It's just a piece of metal out there exposed to water and air, and it'll corrode if it's not protected. Now you can take metal like stainless steel metal and put it out in the air and it won't corrode. Similarly with aluminum, aluminum is already corroded. It has aluminum oxide barrier against it instantly. And so those two metals typically don't corrode. However, the problem is when you put stainless steel and aluminum together, you can sometimes form a galvanic corrosion or battery type of corrosion, where you're forming a battery where you move electrons from the cathode into the anode, and then it will corrode at the anodic end. So the corroded end or anodic end is something you got to worry about. And generally speaking, we use stainless steel fasteners when attaching to aluminum panels. And that's actually a good scenario because the electrons would have to flow from the fastener into the aluminum, and there's just not enough electrons in just a single fastener. However, you wouldn't want to do the reverse, and that is hang a stainless steel panel and attach with aluminum screws, because here you have a wide, huge stainless steel panel that's going to pass all the electrons into those aluminum screws and just corrode them to pieces. So you do have to worry about what type of fastener you're going to spec, what type of materials are going to be touching each other, and are they going to be exposed to water. Sometimes what we do is we just galvanically separate the two metals. Here we have a detail where we have aluminum panels attached with stainless steel screws into carbon steel. And we select isolation tape in this case, just to give, make it so there's going to be no cathodic interaction between the stainless steel and the carbon steel there. Another special topic you should probably be aware of is not all stainless steel is created equal. There's basically 4 different types. 400, 304, and 316 series. Now, 316 series is the best, used for saltwater environments. You'd always want to spec that in case you're near the ocean. 304 is pretty good. You're not going to go wrong with 304. It's about as strong a corrosion resistibility as 316. 400 series, that doesn't come in sheet metal. The 400 series is more used for fasteners. So it was a way to try to harden stainless steel so that it could tap and drill into different materials. Where you see this typically with 400 series is in stainless steel fasteners that attach to concrete or masonry walls. You see those a lot in there. 400 series does have a form of corrosion called hydrogen embrittlement, and it's susceptible to the atmosphere. And you can sometimes get cracks in your fastener, which isn't good. So a lot of jurisdictions actually don't like the use of 400 series fasteners for that reason. So what do we typically use? Well, the bread and butter fasteners that we like to use are self-tapping drill screws. And quick flex and drill flex can get the job done at a great rate. So these are still a steel shanked fastener, but they're coated really thickly with a highly proprietary coating that each manufacturer makes. It's a combination of copper and zinc. And that has a sacrificial anodic piece that's allowed to corrode before it gets into your panel or your screw. So those are the bread and butter. Now, if you're in a saltwater environment or you need something even better in case that coating wears off, they do have the stainless steel 300 series biflex fastener. And now stainless steel, as I mentioned before, is a softer material. So what they typically do is they fuse a hardened steel tip on the end of that so that it can drill through your aluminum. And then they fuse that with a 300 series shank. So you kind of get the belt and suspenders approach with a biflex fastener. They are more expensive. When you're talking thousands and thousands of these screws on a project, it does add up to switch to a all series 300 series stainless steel fastener. Another special topic is tracks and slip planes. So we always want to be sure we're meeting the requirements of the building movements and the building drifts. We don't ever want to cross a rail over a slip plane. Obviously, if the building, everything's attached to the building. So if the building were to deflect and we've got a rail across there, we could buckle that rail and pop our cladding right off. So special care needs to be communicated both from the architectural end on where these slip planes occur and what they're for, whether they're for seismic drift or just vertical downward displacement. We need to make sure we get our joints right, and we need to make sure we break the rails across those joints. Other special topics when thinking about designing your cladding system is know your module sizes for each product that you're using. Here we list some standard module sizes. ACM, typically 60 inch by 193 inch. I wouldn't recommend going a full 193 inch just for thermal expansion. The larger you make that panel, the more it's going to thermally expand, and thus your joints are going to have to grow and get bigger. Typically what we like to see is a max 8-foot panel. That will keep like a 3/8 inch joint typical. If you start getting above that, then you're looking at maybe 1/2 inch joints between your panel sizes. So keep that in mind. Honeycomb, again, 60 inch. Terracotta, this is a clay fired tile. So what you're limited here is what can you fire in the length of the kiln where it won't bow or warp once the drying is finished. And usually that number is 6 feet. If you try to spec an 8-foot long piece of terracotta, you're going to get pushback from the factory that they can't make it that long and keep the tolerances of the bowing within the same effect. Glass panels, 5 feet by 10 feet, typically polycarbonate panels, 4 feet by 8 feet. So yeah, keep the panel sizes in mind. GFRC, of course, there's in theory no limit there because you're casting the concrete. But pay attention just to the joints and make sure that each panel can move within the joint spec that you're providing. Finally, I know we've touched on this time and time again, but I just really want to iterate it here. This is a thermal contraction failure shown on the slide where they basically hard fastened all of the panels together. And then a hot day came along and it warped those panels. I have actually seen buildings where this was an intended effect. The architect did want it to warp for the illusion. But generally speaking, this is not what people want to see. And so we need to be careful when we're speccing really long panels that both the slotted holes can work to expand and alleviate that contraction and expansion, and that you have enough room in the joint separation that you don't close the joint off when they go ahead and expand. And that concludes my special topics. I'll turn it back over to Ilya now. He's going to do a case study.
Thank you, Marty. Yeah, I wanted to finish this presentation with a case study. So last but not least, this is a all-true hospital. It was designed by GLG Architects, and it was in Grand Forks, North Dakota. We did this project with our client, MG McGrath, and what happened on this job is originally for the cladding attachment system, the original design had horizontal and vertical girds. I believe it was a horizontal Z-gird and a vertical hat channel, something like this. And we looked at this project and we asked Marty to do some preliminary engineering, and we were able to figure out a way where we could supply a system that was spanning more, and we're using less material, and it was also an adjustable and thermally broken system. And believe it or not, it was a VE option to the Z-gird, continuous metal Z-girds and hats. And the effect of this was that because of this engineering, we're able to span them every other stud at 32 on center. We reduced the amount of metal by several miles. So the vertical profiles that were supposed to be supplied, we had several miles less. So when we talk about sustainability, obviously the amount of material reduced, that is a sustainable way to build. It was a less shipment, also a lot less labor on site to install these panels. And so this was kind of embodied carbon into the material that went on the wall. And we also improved the thermal performance significantly because they had horizontal continuous metal Z-girds, which are not great thermally. So with using these clips with thermal pads, we're able to improve thermal performance. So to me, this is a perfect case of how engineering helped create a IVE option for a thermally broken system. We're able to use much less material, less labor, and it was a lot more thermally efficient. So at this point, I think this concludes our presentation. Here's some images of projects we worked on, but I don't think we have time to speak about these projects. So I think it's I'll turn it over to Drew for Q&A.
Yeah, thanks, Ilya. Thanks, Marty. We did have a few questions come in. Just as a reminder, if you thought of some questions throughout, didn't type them in yet, just do so in that Q&A box. First question, are the systems seismically stable? Marty, do you want to talk about how we account for seismic loads and seismic design on these systems?
Yeah, these systems are seismically stable. Generally speaking, seismic loads are pretty low unless you're in kind of the Wasatch Front or along the San Andreas Fault, California area. In those areas, we really make sure that the movement of the system parallels the movement of the wall system behind it. So our systems, basically, we want to design them just to float on the wall system beyond, and everything kind of moves with the wall that it's attached to. So we don't want to induce seismic loads on it. We just want our cladding system to slip the same way the building's going to slip and go along for the ride, if that makes sense. So we do look at like the racking loads. I have looked at the racking loads in the tracks before. In particular, we want to make sure the terracotta can slip in the clips. There's studies where we put them on a shake table, some of the cladding systems on a shake table, and they do really well. So
Yeah,
hopefully that answered the question there.
Yeah, and only one thing I would add is the amount of weight of this system could have an impact on the seismic loads on the building. So
yes,
the
yeah,
building
for sure.
designer should be aware of what's going. You know, if it's a metal panel, it's a big difference on the weight of a building than if it's a terracotta panel.
Correct.
And they should know how much seismic weight they should be accounting for in their design. Does oil canning cause long-term damage to the panels or the support system? Ilya, you want to take that one? Or go ahead, Marty. Either one of you.
Oh, yeah, oil canning, yes, there's permanent deformation. So the definition of oil canning is that you do get permanent deformation there. So you could have a hot day, it could warp all your panels, and then they remain that shape. So like I said, I have seen buildings where this was the intended effect. The architect wanted oil canning and a bubbled look, and they got it. It warped and did the intended effect. But certainly, if you want to see a smooth finish, you need to particularly watch out for putting in really long panels and making sure that the documents that are sent, the shop drawings, show the allowed slot difference. Also, if you're going to do really long panels with joints in them, you need to make sure your joint is large enough and calculate how much expansion that's going to occur. So just as a rule of thumb, aluminum, you can go about 12 feet and that will close a 3/8 inch gap. So anything above like a 13-foot module, 12-foot module around there, you're going to have joints that are going to be larger. So things to keep in mind with thermal expansion. It is a thing, and we've got to watch for it on every project.
And Marty, just to add to that, in terms of oil canning, like if it's inherent in the panel, because a lot of times if its panel is very thin gauge, like a 24 gauge metal panel, the oil canning already happens as it comes out of the roller, and it's not even related to the attachments. And I think in general, I mean, these panels will probably stay on the building, right? But that they're not gonna affect, I guess, the backup system, but the effect of the oil canning is not reversible. That makes sense.
Yeah. Well, thanks. That's all the questions we've gotten in so far. I will remind you that if you want to get the credit for this, you can try scanning our new fancy QR code on this slide, or in the Q&A box. There's a new message from Amber. You might have to expand it and click the see more, and then there's a link there at the bottom to go in, and either way you can fill out your information to get a credit there. You can sign up for any of our other great newsletters and stuff like that, and future webinars, which we hope to see you at. With that, again, thank Marty, thank Ilya. Great presentation, and enjoy the rest of your Friday.
Thank you.